Okay, thanks. And I'll join the other speakers in thanking Eric and the other organizers for inviting me to this lovely part of the world. This is my second visit to GGI, and coming back here really brought back memories. My first time was in, I think, 2010 at a similar workshop, and I was thinking about what it was like back then. When you gave a talk on entanglement entropy, you had to explain what it was and why anyone should care. At least in my community, that was the case. So times have changed. So my talk is actually going to be on the same subject as that one from 8 years ago, namely holographic entanglement entropy, which is a subject that continues to fascinate us and that we continue to not really understand, although we understand better than we did 8 years ago. So in particular, one of the ways to kind of think about what we learn from holographic entanglement entropy is how holographic states, which are states of some quantum gravity theory, are special. So that's essentially what this monogamy thing is about, which I'll explain. So we somehow know that they're special, but we don't really have a very concrete understanding of how they're special. And that's the question I'm going to be trying to address. And the tool I'm going to use is this new way of thinking about holographic entanglement entropy called bit threads, which Mike Friedman and I developed a couple of years ago, and which I'll explain. So the good news is that the whole talk fits on one slide. The bad news is it's a very long slide. In the first part, I will remind you about holographic entanglement entropy and tell you about bit threads. This is not, I have a full talk just about bit threads, and I want to tell you about other things today, so I'm going to be very quick in sort of explaining the bit thread story. And then the second part is I'm going to tell you about this inequality, this entropy inequality that holographic states satisfy, which goes by the rather strange name MMI. It's an acronym. It stands for something, okay? Then what I'm going to do in part 3 is bring those two parts together by giving you a proof of MMI using bit threads. Now, we already knew that MMI was true for holographic states, but the whole idea with bit threads is that they kind of give us hopefully a more direct understanding of the information theoretic meaning of these quantities and these properties. And so I'm going to claim in the fourth part that you get that. You get that dividend from bit threads in this case. In other words, that we have a new proof of something we already knew to be true, and as often happens when you have a really new proof from a different point of view of something, that actually brings you some new insight. And so I'm going to claim that what it does is it suggests a very specific, concrete entanglement structure for holographic states. Okay. We start, as always, with the Ryu-Takenagi formula. In this talk, I'm going to be doing just the simplest version, which is Einstein gravity in the classical limit, which is a large N limit from the dual field theory point of view, and just a static space-time, so that the surface in the bulk. So this is a picture of a constant time slice through a static space-time, and I have some region A. And the surface in the bulk, whose area tells me the entropy of A, is simply the minimal surface, which is homologous to A. Homologous means there exists a bulk region that interpolates between A and that surface. Okay. All I'm going to do now is I'm just going to rewrite that same formula in a different language. And to do that, I introduce these objects called bit threads. So a bit thread is just a one-dimensional object in the bulk. Again, in this whole talk, I'm working on a constant time slice, okay? It's an unoriented one-dimensional object. And so actually, let me just say something about unoriented. So in the paper with Mike Friedman, they were oriented, and you kind of have a choice depending on what you're trying to do with them. For my purposes, it's easier just to think about them as being unoriented. So we're just going to do that. It's a little bit simpler. Anyway, the most important things you should know about bit threads are that they obey two rules, okay? And they're extremely simple rules. And they're rules which are what connect the bulk geometry to the information theory, okay? So, and the rules are simply that the threads don't split or join, and they don't end anywhere in the bulk. So so every thread, if it has endpoints, I mean, you could have little loops, but they don't really play any role. But if it has endpoints, those endpoints are both on the boundary. You could also have a horizon, and they could end on the horizon also. I'll talk a little bit about that later. And the second rule is that they know the geometry. They're sensitive to the geometry because they have this rule that the total local density is bounded above by basically 1 per Planck area. And so if you want, you can think of the threads as having a cross-sectional area. Each thread is having a cross-sectional area of 4 Planck areas. But you should know that, I mean, let me just emphasize for those of you who don't necessarily work in this area that in the natural units for describing the geometry, there's sort of a macroscopic geometric scale and a microscopic geometric scale. So the macroscopic geometric scale is like the curvature scale here, and the microscopic one is the Planck scale, which, as suggested by the name, is much, much smaller. So this is a very, very large numerical density from a macroscopic point of view. So the threads are extremely microscopic. They're Planckian, and there's many, many of them, in any given region from a sort of macroscopic point of view. Do they have true starting at the same time? Right. So in this talk, that's a good question. In general, the answer is no, but I am going to work on a single time slice, so everything I do is going to be on a single time slice. And in this talk, they have to begin and end on the same time slice. Okay, and so then what do you do with these threads? So it's very simple. So let's say you want to know the entropy of A. So you just so every thread that connects A to its complement is basically going to contribute 1 or log 2 to the entropy, okay? And so if you want to know the total entropy, you just put as many as you can, but subject to these two rules. So you put as many threads as you can connecting A to its complement until you can't anymore. And why can't you anymore? You can't anymore because somewhere you're saturating this bound, okay? And where are you saturating this bound? You're saturating this bound on the minimal area surface. Okay, and that's why it happens that the maximum number connecting A to its complement is equal to the area in Planck units of that minimal surface. Okay, so it's incredibly intuitive. It's pretty close to being obvious when you think about it in the right way. But of course, like many things that are obvious, it's still important to prove them because there's also a lot of things that are obvious in math that are not true. So. But anyway, this one is obvious and true, and there's a theorem behind it, which is a Riemannian geometry version of the celebrated Maxwell-Min-Cut theorem in network theory, and it has a beautiful proof using tools from theory of convex optimization. Okay, so we have a version of, so this is completely equivalent to that. We have a version of Ryutake Yanagi, which is just in a different language, so we can basically forget about minimal surfaces. Okay. Now there's a few facts that are very, very important to know. So the first one is that, so I said that the thread configuration is highly non-unique I said that the thread configuration is tightly packed on the minimal surface, but away from the minimal surface, you are not saturating that bound up there, and so there's a lot of freedom. So these threads are very floppy, they can move around, and in particular, the place where they end on the boundary is not at all fixed, and that's crucial. So you might think from a picture like this, if you just look at one picture, there is something about laser pointers, I have to say. So you might think that, oh, great, now I totally understand, it's so simple. There's a bit here which is entangled with a bit here, and such a simple, quantum state. And of course, that's totally bogus. I mean, we know that field theories are not like that at all. And so how is that consistent with this? Well, it is not ever, the interesting thing is not ever one thread configuration, but the set of thread configurations that achieve the maximum for a given A. And so it's, in fact, the leading role in this talk will be not any given thread configuration, but the freedom in choosing different threads. So the flexibility of the threads is actually crucial. Okay, and so again, even though from an enumerative point of view, each thread represents an entangled pair of qubits, you should not at all think of them as being localized, okay? Okay, and then what we argued is that using this freedom, you can write very nice formulas. I mean, okay, so in terms of minimal surfaces, if you want something like a conditional entry mutual information and so on, of course you get like sums and differences of areas, and it's not really clear what those have to do with the quantities in question. Whereas with the threads, you kind of get a very nice like one-to-one correspondence between certain numbers of certain threads represent the conditional entropy, other threads represent mutual information, and so on. So I'm not going to go through that. You'll see some of that story today, but and you can also prove important properties like subadditivity, strong subadditivity, and so on using the threads.
But how many such thread configurations are there? Those who are entry back?
There's lots. I mean, yeah. Yeah. I mean, what do you mean? I mean, there's an infinite number, but I mean, everything is continuous here, so.
So is there a way to measure it?
Oh, it's very wild. It's very wild. I mean, so that's in some sense, it's a little bit of like the space of thread configurations is like some huge infinite dimensional space. It's some functional space, okay? Yeah.
Sorry, and you don't make them in geodesic, or if you try to do something like that, like make them geodesic?
So, right, so there's another story I could give a talk on, and people are thinking about this. You could say, this is, in some sense, the freedom to move the threads around is some kind of gauge freedom, and you could say, it's too wild, I kind of want to gauge fix a little bit. And there are ways to gauge fix, to sort of add conditions beyond those rules that nail down a particular one, and having them be geodesics, you can do that to some extent sort of piecewise, and in very simple situations you can just make them geodesics, but not in general. And then there's various different ways to gauge fix, yeah, but let me not go into that, yeah.
Is that something?
So, yeah. So indeed, so far I just have a single A, and in the rest of the talk, it's going to get more interesting because I'm going to have A, B, C, and then we're going to talk about, well, what are the threads going from A to B and stuff like that. So that's the whole rest of the talk is just about that. Okay. Indeed, the whole point is it gets much more interesting if you say, I care where they end. I'm interested in some other region B, and I care how many of them are going from A to B, and how many of them are going from A to C, and I want to keep track of those, and what do those numbers represent, and so on. Okay? And things I'm not going to talk about, but that I could talk about in terms of bit threads. So there's a bit thread version of this entanglement of purification story we heard about couple days ago. You can add higher derivative corrections, and that's something I'm working on with my students. There is to answer a question about time, there is a covariant version, which I'm working on with Veronica, and then there's sort of, you can prove a Lorentzian version of min-flow max-cut. And all of these are generalizations of Riemannian max-flow min-cut theorem. So there's actually a lot of, I think, really beautiful, interesting math having to do with applying convex optimization theory to geometrical problems, which I just basically, I'm going to just hide today. Okay, all of the mathematical machinery that actually makes this work, I'm just going to, cover the hood. Okay, so so now I'm going to switch gears and set up the problem, the thing we want to understand using bit threads, and that's this MMI. Okay, so you all know mutual information. You know that it satisfies these inequalities, subadditivity, strong subadditivity, and those are true for general quantum states. But then there's an inequality that's special to holographic systems, which is this one, which should have been called superadditivity of mutual information, but we called it monogamy of mutual information. And superadditivity of mutual information because it's just saying that not only is the mutual information between A and B, C larger than that between A and B, which you know from strong subadditivity, but it's actually superadditive, and you can rewrite it in terms of the entropies, and when you do that, you see that it's actually permutation symmetric under exchanging A, B, and C. So Alex Maloney and Patrick Hayden and I proved this a while back. By cutting and pasting minimal surfaces. So when I say proved it, what I mean is you assume the Ryutake-Yanagi formula and you show that it follows from the Ryutake-Yanagi formula, okay? There's some argument, this is some diagram I took from our paper, where to just sort of illustrate how it goes, you look at minimal surfaces corresponding to the left-hand side and their total area, and then you kind of cut those up and glue them together and get some other surfaces which have the right homology conditions for the things on the right-hand side, and so you get the inequality. I'm not going to go through when you actually write it out, it's much more complicated than this picture suggests, but anyway, it takes like a page to write everything out. Like most of the proofs of properties of entanglement entropy you get from Ryutake-Yanagi, it's somehow, well, I find it a little bit opaque. It gives the flavor of being sort of like a coincidence that minimal surfaces have these properties. Okay? You had a question, Mark?
Yeah, just can you remind me, so it's not true in general systems, in 3-qubit systems, is there some particular class of states that violate it?
I'm definitely gonna,
okay.
Yeah. So the next thing is that this inequality is not true for general quantum states. And so this is actually what we like. This is why this is the simplest property that you can write down that holographic states have in terms of entropy, simplest entropic property that holographic states have that's special. Okay? And so it's definitely telling us something about holography and therefore telling us something about quantum gravity and all of these big questions, right? So, so I'm going to give an example of a state of a quantum state that violates it. Yeah.
Should this be valid also for Mera states since they
Yeah. So it's also valid for some class of tensor network states. I mean, it's not valid for all Mera states because it's not valid. For example, if you just take some field theory like a CFT that's described by Mera, it's not valid for those field theories. So it's not a property of tensor networks. It's a property of certain tensor networks. Okay? Okay, so to understand this inequality, let's just take the difference between the left and the right-hand side. And so that's just this minus this, or this minus this. And It's called the tripartite information. It's called minus I3. If you want to know why is it called minus I3, you should ask Horacio. He named it that. No, well, you called the other one I3, yeah. So, okay, so what is this minus I3? Okay, so first of all, what I'm going to do is I'm going to purify my ABC system, which I can always do holographically. If I was in a mixed, like a black hole state, I could do the thermal field double, and that's the two-sided black hole, so I can always purify my system holographically. So then from the rest of the talk, I'm going to assume the full system is pure. That's a convenience, okay? There's nothing deep about that statement. So then first of all, minus I3, when you write it out, you see that actually it's fully S4 symmetric, not just S3 symmetric, and therefore I'm going to stop writing the argument ABC because it's the same no matter which three you pick out of A, B, C, and D. And it's sensitive only to fully four-party entanglement. So what that means is that if your pure state is just a tensor product of a pure state on AB with a pure state on CD, or a pure state on A with a pure state on BCD, then it's easy to see that minus I3 vanishes. So it only picks up the fully four-party entangled part of your state, basically. Okay? It can be either positive or negative. So the simplest case where it's negative is the four-party GHZ state, where if you just work it out, actually the easiest, well, anyway, let me not do that in real. It's a very simple exercise to just calculate minus I3 for this pure state, and you get minus 1. And so therefore, this state does not obey MMI, and so this state is not a holographic state. It's not a holographic state anyway because it has a tiny entropy, but if you had, let's say, a huge number of GHZ states, that could not be a holographic state. On the other hand, something which obeys it is the perfect tensor state, which, so what is a perfect tensor state? I'm not going to properly define that, but for our purposes, it's just one where the entropies of all the single parties are equal, let's call it S naught, and some positive numbers, and the two-party groups have just twice that entropy, which means that all the mutual informations, let's say between A and B, so on, those all vanish. And then if you compute minus I3, you see it's 2 S naught. Okay? So this is kind of the simplest type of state that has a positive value and therefore has a chance of being holographic. Okay, and so somehow as an experimental fact, okay, to the extent that we take this as our fundamental dichotomy, which is kind of an unfair way of, I mean, we had this talk a couple days ago about, all the different crazy kinds of entanglement you can have when you have more than two parties. And here I'm being incredibly reductive. I'm just dividing it into two categories, either GHZ or perfect tensor. So because one has positive and the other has negative value. So to the extent that you take these as examples of four-party entanglement structures, it must be the case that the perfect tensor type entanglement dominates over the GHZ because the total is positive in holographic states. Yeah.
If I just had a bunch of EPR pairs plus a bunch of three-party GHZ things, does that give me 0 or something? Or?
Anything which is not fully four-party gives you 0. Yeah. So three-party GHZ, three-party W, two-party whatever, all that stuff does not contribute to minus I3. Okay. Now, it's helpful, actually, when talking about these entropies to kind of change coordinates a little bit because we're talking about linear inequalities, and so we're just going to use a different set of coordinates. So when you have n part, one thing I've learned about talking to quantum information theorists is these people really like parties. You have, if you have an n-party pure state, the number of independent entropies you can count is 2 to the n minus 1 minus 1. So for example, if you have two parties, then there's just one, because you know S of A equals S of B, and that's the same as this half of this mutual information, and any positive non-negative value is allowed. With three of them, these are independent, but S of AB equals S of C, so that I don't get more of them. I can also just do a linear change of coordinates and write the three mutual informations, and that's actually useful because all I have to do to get a valid set of entropies is just choose non-negative numbers for these three numbers. So in these coordinates, it's just the positive octant, which is the allowed entropies. Now with 4, there's 7, because I have A, B, C, D, AB, which is equal to CD, AC, which is equal to BD, and so on. So now I have 7 independent entropies, and I can do a change of coordinates to the mutual informations, but there's only 6 mutual informations. So what's the 7th? Well, the 7th is minus I3, and if you look at all of the constraints on the entropies, like they have to be positive, subadditivity, strong subadditivity, and so on, then if you include the MMI constraint, which is positivity of this last one, so we know from subadditivity all of these have to be positive, and it turns out that's not only necessary but sufficient. So if you give me 7 numbers that are non-negative for these quantities, that is, and then then that will satisfy all entropy inequalities. In particular, you might worry, well, how do you know it satisfies strong subadditivity? Well, it's very easy to see that these two things imply SSA. So basically, this is a nicer set of coordinates for the space of entropies than this, although they're equivalent, because the inequalities satisfied are easier to write down in terms of this, just positivity or non-negativity. Okay? All right, so we're going to use that handy fact. Oh, by the way, you might wonder what happens for more parties, and the only thing I'll say there is that it just gets really complicated. It does not proceed in a like simple. Well, the n equals 5 case is still under control, but once you get to 6, it gets really nasty and it's not really well understood. And so in this talk, I'm not ever going to go beyond 4. Yeah. What's that? Say it again. No, there's no simple, so we have a set of linear inequalities which carve out a cone in the space of entropies. So we have this 7-dimensional space, and then there's a cone which is carved out by all of the inequalities. The holographic cone sits inside of the quantum cone, and the quantum cone is just the ones allowed by, you just drop this one, but you can't really write it in such a easy way, that's all. It's not just this sort of octant in the 7-dimensional space anymore. But I mean, yeah. So it's simpler. The holographic cone actually is sort of simpler in that sense. Okay, so now what I want to do is to prove MMI in the language of threads, and I mean, as often happens in physics, the way to make progress is simply to find the right theorem proved by Russians in the 80s, right? So that's what we're going to do. That's how we're going to solve this problem. That theorem has to do with something called multi-commodity flows. So basically, if you know anything about max flow min cut, it's about basically how much stuff on some network you can move from a source to a sink. And so if you think of the network as being like a rail network or whatever, and then, on your rail network, you might not just want to move, coal from one place to another, but on the same rail network, also potatoes from some other place to some other place. And so if you're like a Russian economist doing a centrally planned economy, you want to understand how on the same network, you move things from different sources to different sinks at the same time, right? Subject to this total capacity, for each link on the network, okay? And so those things are called multi-commodity flows. The sort of basic theorem about them is the one I'm going to state now. It's a very beautiful and somehow a little bit surprising theorem, which I'm going to state in the language of Riemannian geometry, but it's obviously it was originally proved in the network context. So you have any number of regions on the boundary, and I'll state it in the language of thread configurations. There's a thread configuration that saturates, so any thread configuration, the number of threads connected to any AI is at most S of AI. That's the definition of S of AI. So there's a thread configuration which manages simultaneously to saturate all of those bounds for all of the AI. Okay? It's actually very surprising that this is possible. And so I'm going to give examples in case that wasn't clear what I mean. So here n AI aj is the number of threads connecting AI to aj, and the total over j not equal to I is equal to S of AI, which is the maximum possible connected to AI, connecting AI to its complement. Okay, so this was proven in the 80s in networks using some techniques that do not carry over to the continuum Riemannian case, and so we had to prove it from scratch. And I think it's a very beautiful proof. It uses, again, these tools from convex optimization theory, but I don't have time to go into that. Yeah, so for a given thread configuration, there's some number of threads connecting region AI to region AJ. That's n AI AJ. Okay, maybe examples are probably more useful than words here. Although the first example is not so useful because it's way too trivial, which is n equals 2. This is just the picture I had before, but where I called the complement B. But when you have n equals 3, then you now have 3 types of threads. You have the ones connecting A to B, the ones connecting A to C, and the ones connecting B to C. And what the theorem states, that equation up there, if I just write it out, is that if you look at A, the total number from A to its complement, of course, is the number from A to B plus the number from A to C, and that is equal to this number being the maximum total you could ever have connecting A to its complement. So you manage to saturate that inequality. Not only do you manage to saturate that inequality, but you also saturate the corresponding inequality for B and for C. So this amazing thread configuration calculates for you all of the entropies. This one thread configuration, okay? And then it turns out that it's not too hard then to calculate like this mutual information, which is just this plus this minus this, because S of C is equal to S of AB. And then if I don't know how quick you are doing it in your head, but you get 2 NAB. So it's saying that these threads from these threads, the one that go from A to B, are counting for you the mutual information, each one contributing 2, just like a pair of qubits, putting aside factors of log 2. Okay. And same, so the threads connecting A to C are calculating the AC mutual information and so on. So by the way, so this proves subadditivity because, of course, these numbers can't be negative. Okay, I mean, there's much simpler proofs of subadditivity that don't use this fancy theorem and so on. But, okay, so what about n equals 4? Now my picture drawing skills break down. So let me just draw the 4 as just points on a tetrahedron, and then we have 6 sets of threads, A, B, A, C, and so on, okay? And now it's saying that the number coming out of A is equal to S of A, so there are 3 terms now. Now, if we want to compute minus I3, we need to know not just S of A, S of B, S of C, S of D, but also S of AB, S of AC, and S of AD. So let's look at S of AB. Now, you might have said, oh, no problem. I'll just look at the total number of threads coming out of A union B, which is BC, BD, AD, and AC, right? Connecting AB to CD. Those are the 4 terms. But here you have to be careful. So there you would be wrong, because what the theorem, although this thread configuration is very magical and it computes the entropy of all the individual regions, it does not calculate the entropy of unions of regions. That would be asking too much. So this is not necessarily equal to this. But it is an allowed thread configuration, and therefore the number that you get cannot be more than S of AB, which is by definition the maximum possible from AB to CD. So you get an instead of getting an equation like you get for S of A, you get an inequality. And then you just do all the permutations, add them up, and I hope you'll trust me, that's a very simple exercise. You get MMI. Okay, so MMI just follows straight from this. It's an almost trivial consequence of this theorem. Okay? Now, if you start thinking about this a little bit, you might be upset about something, because here it was very beautiful. So now we get, okay, in some sense, right, the non-fluffy part of the talk is over. Okay. I've achieved my goal, I've proved the theorem. Okay, but of course, we want to get some insight from that. So now you start thinking about this a little bit more, and you might be a little bit unhappy, because the beautiful thing here was that I could say that these threads are representing entangled pairs of qubits, and that's why the number of them is equal to the mutual information. But here, I have these threads, and the number of them is not equal to the AB mutual information. All I have is an inequality. Okay. I don't have an equality. So there's like extra threads here that are connecting A to B that are not representing the mutual information. So here, the important thing, again, is the freedom. So in this case, the numbers were fixed, the ends were fixed once you knew these entropies. But that is not the case here. The entropies do not determine the ends. There is freedom in this thread configuration. And that freedom is kind of the whole point in some sense. Okay? Let's look at a simple example. So now I just go back to a graph. This is a very simple graph, and I just have capacity 1 on each leg, and I ask, okay, what are the thread configurations here? There's 3 of them. I can either connect A to B and C to D, or any other way of doing it. If you calculate the entropies, you find that this is basically a perfect tensor state that has minus I3 equals 2. Okay, it's a perfect tensor state because S of A, all the individual entropies are 1, and the unions AB has entropy 2. Okay? And so what we find here is that, so this is a case where there's no mutual information at all between pairs. And so what are the threads doing? Well, they're switching off. So instead of a thread leaving A can go to B or C or D. And the number of threads that can switch off is precisely minus I3. Okay? So here, in this case, we just have 2 threads that can switch off in this way, and that number is minus I3. Okay? So the content of MMI in the thread language is that you have some threads that are not fixed where they start and end. Okay? Okay, let's try to get a lesson from that in terms of the structure of holographic states. So first of all, so I'm just going to build up from, the two-party case. Okay, so in the two-party case, there's almost nothing to say. It's simply a fact that, by definition, that's a bipartite pure state, and the amount of entanglement is the number of threads connecting A to B. For n equals 3, what the picture looks like is that based on these equations that we had before, we have only bipartite entanglement. In other words, there's some part of the A Hilbert space and some part of the B Hilbert space which together are in a pure state. The rest of the A Hilbert space with some part of the C Hilbert space together are in a pure state, and the rest of the B Hilbert space and the rest of the C Hilbert space together are in a pure state. And there's no tripartite entanglement. Now, and I should say that here again, it's very important that to emphasize that this decomposition is not by spatial regions. It's not that you divide A into two parts and one spatially, and one part of A is entangled with one spatial part of B, okay? Because I have all this freedom in where the threads end. I could have had this one end here and this one end over here, and so there's no significance to the place on the boundary where the thread ends. Yeah.
But that's not strictly true. I mean, the actual holographic state.
Yeah, I forgot to say something. So this might address your concern. So I should have emphasized, sorry, that what I'm talking about now is in a large N sense. So it's not in, this is this is definitely not true. This equation is definitely not exactly true, for sure. Was that your concern? Yeah. And actually making precise what I mean by this large N sense is an open problem. So I'm giving myself that wiggle room. Okay. So this is a completely trivial statement. This is a very strong statement. It's not just saying there's no GHZ or no W, there's no tripartite entanglement, at least at leading order in large N. What's going on? If four parties, well, do I want to keep saying there's only bipartite entanglement? Well, that we know is not true, because there's also definitely this four-party entanglement. So now this four-party perfect tensor entanglement. So now what I want to say is the bit thread suggests basically, there's two types of threads. There's the ones that go from A to B and that have to go from A to B because those represent the mutual information, and those give you bipartite entanglement. And same for A to C, A to D. So there's 6 of those. And then there's the ones that switch off. The number of those is minus I3. And those together represent a four-party perfect tensor. Okay? So we have a decomposition of A into 4 parts, a part which is in a pure state with some part of B, a part which is in a pure state with some part of C, and so on, and then a part which is in a four-party perfect tensor state with part of B, part of C, and part of D. Okay? And the point of this structure is that it makes MMI manifest. Okay? If this is true, then MMI is not mysterious at all. It's just completely obvious. Okay? Because the two-party pure state parts don't contribute to minus I3, and you're just left with the perfect tensor, which has a positive value of minus I3. Okay? And again, the strong statement is that there's no tripartite entanglement here. And let me just give, in case this sounds wildly implausible, this n equals 3 claim strongly constrains anything you would do at n equals 4, because if I claim there's some n equals 4 structure, I could take 2 of those parties and just consider them to be a single party. And so it has to reduce to something which has no tripartite entanglement. Well, if I had a GHZ state at n equals a 4-party GHZ state, and then I merge 2 of the parties, what do I get? I get a 3-party GHZ state, which I said is not there. So it's only very special 4-party states that reduce in the right way under merging. And what states are those? Well, those are the perfect tensor states. So if you take a 4-party perfect tensor state and merge 2 of the parties, you end up with something that looks just like this. Okay? So it's consistent, at least I'm being consistent. Okay? And as a final piece of evidence, Michael Walter and Sepper Nizami showed that in these, I'm basically done, that in these random stabilizer tensor network models of holography, you get exactly this structure at leading order in large N. There's no tripartite entanglement, there's no GHZ type entanglement. The leading part of the entanglement is just perfect tensors and bipartite. Okay? So to the extent that you believe in tensor network models of holography, you can consider this as a piece of supporting evidence. Okay. And then what is there to do? Well, I could have made a longer list, but the sort of most urgent things may be, this, as I want to emphasize, is a very strong claim. It could be completely false. Just wait till we get the paper out before you put your paper out saying that it's false. But it's, I think it's important to test it. And then the other thing is to better define it in the sense that I haven't been precise about what I mean by large N. Okay? And that's very important to do. And then, of course, the generalization to more parties seems very hard. We don't have a good set of tools for that. And that's it. Thanks.
Time for one or two questions.
What happens when there are transitions between minimal surfaces? In particular, the entanglement entropy is usually continuous, but it's not smooth. So is it possible to see this feature in this language?
Yeah, I would have said it's one nice thing about the threads is that when a transition like that happens, the threads themselves are continuous. The only thing that happens is that the bottleneck jumps from one place to another. But the thread configuration changes continuously. So I think that's, it sort of, these transitions kind of somehow suggest that the location of the minimal surface should not be considered as a very special place. And that's kind of reflected in the threads where the thread configuration itself is continuous.
But it's not smooth, the entanglement
The
entropy.
number of threads is not smooth.
Oh.
Yeah. Mm-hmm.
All right.
I
Any
think
others?
Mark.
So just to clarify, so when you're talking about perfect tensors here, you're meaning just some properties of the entanglement entropies for the various parties. Can you say again exactly what you mean by?
Yeah.
I mean, you're not actually talking about having necessarily a perfect tensor.
Right. So I guess the correct definition of a perfect tensor is that you have maximal entanglement across every partition, of course, that assumes that you know the Hilbert space, and of course we never really have maximal anything because we're in some big infinite dimensional Hilbert space. So it could be an actual perfect tensor then tensored with some boring pure state, local pure state. But the only thing I actually used, where'd it go, is this.
All right. I think we should probably move on. Oh, okay. Quick question.
Right. So what we found is that okay. So first of all, I should say for those outside the field that one is interested in not necessarily having Einstein gravity in the bulk. You could have some higher curvature terms, and there are some things that are known about how the entropy, the Ryu-Takayanagi formula, gets corrected, and so we can reproduce those corrections by changing the norm bound, by basically changing the second rule. If you make the second rule more complicated so that the bound on the density depends on what the threads are doing, then you can reproduce those corrections.
Okay, I think we should move on to the next talk. But thank you.